Hello students, so the next theorem for finding moment of inertia of a body, if you already know the moment of inertia through some other axis for the same body, that is your perpendicular axis theorem. Now you should be very carefully applying this theorem because this theorem is applicable only for laminar bodies, meaning to say bodies which are flat, 2D, almost 2D bodies. They are not having any depth. The depth is negligible compared to the area of the body. So I'll just tell you what the theorem is, and then we'll do a quick proof of that theorem and see where all it can be applied. So suppose you have a body which is absolutely flat. It is in this dimension of the board. It's not 3D. That's the body. And suppose you know the moment of inertia through any two axes of the body which are perpendicular to each other. So these two axes need to be perpendicular to each other. So let me call this axis as x-axis and this axis as y-axis, and the moment of inertia about the x-axis for the body is say ix, and about the y-axis is say iy. Then if I want to find the moment of inertia of the same body about an axis which is perpendicular to both x and y, and it is going outside the board or inside the board, it is in the third dimension. So axis which is perpendicular to x as well as y. So same as your coordinate system, your z axis will serve for that, x and y. So that's your z axis which is outside inside. So if you want to find that moment of inertia about that body, about that axis, that is iz, then the relation is ix plus iy will give you iz. Looks like a very simple relation, but there is a lot of scope where you can go wrong. So we'll just quickly derive this before we discuss where all you can get caught and you can go wrong in this. So why is this formula holding true? Why is it holding right? So let me just make few point masses which is contained in this mass. So ultimately your moment of inertia about any axis is integration or addition of all the m into distance squares. So let me not take all the masses but few, and those will serve good enough for considering the whole mass as such. So let these masses be m1, m2, say m3, m4. You can take any number, 1 or 2 would be enough to show you what's happening. So I'll just take my m3 over here because m3 was coming in the way of m1 when I dropped the axis. Now the distance of m1 from the x-axis is say y1, because I am assuming the coordinate of this to be x1 comma y1. Because these two axes are perpendicular, it serves as good as a coordinate axis. So this distance is y1, this distance is x1. Similarly, this distance would be y2 if the coordinate is x2 comma y2, and that distance would be x2. Similarly, this one, the coordinate is say x3 comma y3. So x3 itself is a negative quantity. This distance would be minus of x3. The distance value would be minus of x3. The distance is the mod of the value. So x3 was a negative, minus and minus of x3 is x3. You can call it as x3 as such, doesn't matter in this case at all. And this is your y3 distance. Now suppose I ask you what is the moment of inertia of the body about the x-axis. So what would you write? I'll write that over here. Ix, what would that be? m1, then the distance from the x-axis, which is y1. So y1 square plus m2, y2 square plus m3, y3 is the distance from the x-axis. So y3 square dot 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 for all the masses. What about moment of inertia of the body about the y-axis? So what is it? m1 x1 square. So distance from the y-axis is x1. For the next one it is x2, and for the next one is minus x3, but the square of it, if we do the square, then we don't care about the negative and the positive sign. It becomes positive as such. So it is m2 x2 square plus m3 x3 square. You can write a minus of x3 whole square, dot 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 dot. Now if I ask you what is the moment of inertia of the same body about the z-axis, then what will you do? I'll get another color. The distance is from the z-axis, that's your z-axis. So the distance from here, so that's the shortest distance, that is inside out. So the shortest distance is this. So any other distance on the z-axis will be the longer distance. So you take the shortest distance. Your x2 was the shortest distance from y, your y2 was the shortest distance from x-axis. So the shortest distance again are these of the 3 points. So what would you write? So your I about z-axis will be m1 into distance of m1 from the z-axis, which is this green line, which is how much? Which is your x1 square plus y1 square under root. So that length is x1 square plus y1 square under root, and you have to do a square of it. So what do you get? x1 square plus y1 square. Yeah, you do under root and then you do a square of it. So okay, I'll write under root and I'll write a square of it. Similarly, m2 would be what? This distance. So that distance is y2 square plus x2 square under root of that. So square of that, x2 square plus y2 square. Next one, m3 similarly would be x3 square plus y3 square, dot dot dot. So what do we get? What do we see? We see that Iz is equal to m1 x1 square plus m1 y1 square plus m2 x2 square plus m2 y2 square plus m3 x3 square plus m3 y3 square, which is nothing but addition of ix and iy. So very easily we are seeing that Iz is equal to ix plus iy. So that's derived. So this equation stands for a laminar body, a body which is not having any depth. So why will it not hold good for bodies which are having depth? So let me take a mass, suppose it was having some depth or some height, and I consider a mass over here, somewhere over here. Now what is ix? Ix will be this distance square into whatever mass it is, say m4 into this distance square. Okay, well and good, that is your ix. What is your iy? Iy is m4 into that distance square. Okay, that's also well and good. Suppose the height was z over here, then this distance square would be y4 square plus z square, and that distance square would be x4 square plus z square. Now what is Iz? Iz will not be a distance from here to there. Even if it was, it won't be an addition of these two. Iz would be a distance from here to the axis over here. Yeah, so if you want to find Iz for that mass, it would be this distance, the tip of this blue marker to the tip of the green marker, that will be the distance, which is y4 square plus x4 square will be the shortest distance, that's the base distance, will be the tip distance of the z-axis from the tip distance between the two markers. So it wouldn't have the z in it. So I'll just repeat what I was saying for you to get it more clearly. I have taken another mass of the same body, so I'll just draw it over here so that it doesn't make a mess. That is suppose m4, and its coordinates are x4 comma y4 comma z, or z4 if you want. So that is having a height of z. Now what would be ix for this? Ix for this would be m4 into the distance between the tip of the blue marker, which is over here, the body is over here, to this x-axis, to the x-axis. So the height is z, and this base length is y4. So it would be z4 square plus y4 square. So z4 square plus y4 square under root and square of that. So that will be ix. Similarly, iy will be distance of the tip of the blue marker to the y-axis, which will be equal to this base length square, which is x4 square plus z4 square again. So m4 into z4 square plus x4 square. And what would be iz? Iz would be the distance of the tip of the pen to the z-axis. The shortest distance to the z-axis is the direct distance over here. That's the direct distance. So that is this base distance. Whatever is the distance of this point from this origin will be the distance of the tip of the blue marker to the tip of the green marker over here. So how much is that? So that is your m4 times x4 square plus y4 square. So we clearly see that your iz is not equal to your ix plus iy in this case. Hence it is kind of a proof that if it is a three-dimensional body, a body is not in the same plane, then your iz is equal to ix plus iy doesn't work. So that is one of the important criteria of perpendicular axis theorem, that it has to be in the same plane. So I hope it is clear that perpendicular axis theorem is only for a flat body, a laminar body. It is not for bodies which are having depth. And then the two perpendicular axes which you are adding should be in the plane of the body. These two should be contained in the plane of the body. They need to be perpendicular to each other and should be in the plane of the body. These two should be in the plane of the body, and the third perpendicular axis. All three are perpendicular to each other. X, Y, Z are all mutually perpendicular to each other. This third perpendicular axis should be normal to the plane. This one needs to be normal to the plane, and then only the law works. It is not like you'll add any two which are perpendicular and get the third one. That's wrong. If ix plus iy is equal to iz, then obviously ix plus iz is not equal to iy, and iiy plus iz is not equal to ix. It is not like any two perpendicular added will give you the third one. Not at all. The two which are in the plane has to be added to give you the third one. Next salient feature is these two axes may not be going through the center of mass. This point need not be the center of mass. So while we were proving, it didn't matter that this point is the center of mass or not. It is just that the two axes which are perpendicular to each other are crossing. The third axis iz has to cross the same point where the two axes which are in the plane are crossing. Now I'll just give you an example where students actually go wrong, and to emphasize the same point which I have said earlier, if there is a cube, say all sides are A, it's a cube and all the sides are A. Now if I ask you what is the moment of inertia about an axis which is going through the bulk of the cube, it is going through the bulk of the cube, and what is the moment of inertia about that axis, and you say it is, suppose, iy. Then I take another axis which is going like this, again through the bulk, about the center of mass, crosses this, comes out. Suppose the moment of inertia about this axis is ix, and then I take a third one which is going from outside to in. It's like a 3D thing and goes out from behind. and suppose the moment of inertia about this axis is Iz. Now by symmetry we can easily say that Ix is equal to Iy, because when I do the integration and when I do the mass distribution, look at the mass distribution about the x-axis, it is having the same mass distribution what is there about the y-axis, and in fact it is the same what is there about the z-axis also. Then can I write that Ix plus Iy is equal to Iz? That's absolutely wrong. Absolutely wrong. That's absolutely wrong. This is right, that all the three will have the same moment of inertia. It's a 3D body, and your Ix plus Iy is equal to Iz won't work over here. So a clear demonstration that your perpendicular axis theorem is applicable only for laminar bodies which are having very shallow depth compared to its cross section. Okay, so 2 points. One is may not be Cm, your Ix and Iy may not be ICMX and ICMY, and the other one is that the perpendicular axis which are in the plane needs to be added to get the third one. So let us just see, just do 1 or 2 examples where it is applied, and then I'll ask you few where you will have to tell me whether you can apply this theorem or not. So first thing would be to understand whether you can apply the theorem in a particular case or not. If it can be applied, then only you will follow it up by this theorem and solve the question. Yeah, so first question, suppose it is known to you that for a ring, it's a ring, your radius is r, your mass is m, and it's a ring. So what is the moment of inertia about an axis which is going out of the plane normal to the plane as shown? So I'll call that axis as z-axis. So what is the moment of inertia? So that's already known. So I'll write it over here. Iz is equal to mr square. I hope you remember this. All the masses, all the point masses, or all the elementary masses were distributed at a distance r from the axis of rotation. So it was all those elementary masses into the same radius square, r square. So gave you mr square. So that's your moment of inertia of the ring. Now if I ask you what is the moment of inertia of ring about a diametrical axis, which is along the diameter of the ring, any one diameter. If I ask you that, so I'll call it as, say, ID. Then obviously that is also a Cm. It is also moment of inertia about the Cm, but the axis is different, and this Iz was also Cm. So this we have already emphasized that there are several moment of inertia through Cm. So ICM is not necessarily one value for any given mass. It has got infinite values depending on which axis we are talking. So generally we talk about axes which are in the plane or perpendicular to the plane of the body if it is a symmetric body. Okay, so how to get it? So I'll give you 30 seconds, just do it. So I hope you got an answer. Obviously this is being discussed under perpendicular axis theorem, so your mind will go towards it. So we know the plane of the body is this. We'll draw two axes which are perpendicular. One was the asked axis, and we'll draw the other axis, another diameter, I'll call it as d dash. So these two are the perpendicular axes which are in the plane of the body, and the one which is outside is already given, which is your Iz. So what we have here is the equation above with the help of the perpendicular axis theorem is ID plus ID dash is equal to Iz. ID plus ID dash is equal to Iz. Now this is known, these two are not known, and this was asked. But by symmetry, I can say that this value will be same as this value, because had I done an integration taking this axis and did the distribution of the mass and x square added those, and if I do this, I'll get the same result because the distribution about these two axes are symmetric. So what we can say is the value of this will be the value of that. Hence, we can write 2id is equal to your iz. So that solves the question. Your iz value was mr square. So you get id is equal to half mr square. So that's also through CM. So very simple application. This is a known value. So in the list of formulae, this might be given as a thing to remember as this was given. So this is a simple application of your perpendicular axis theorem, and I would encourage you kids to quickly get the same thing without the theorem and through integration, just to have a practice on the integration. So I'll just wait for a minute and hope you do it. What I'm asking you to do is get your ID without the perpendicular axis theorem. So, okay, I hope you have got it. Take a elementary mass dm at an angle theta. The span of the elementary mass is d theta. Hence, the value of the elementary mass will be m divided by 2 pi into d theta. So total m by total angle into the angle it is covering. So that's your elementary mass, and the distance of the elementary mass from the axis in question would be r cos theta. That is this distance which is your r cos theta. So what we have is your di would be equal to dm, which is m d theta by 2 pi into r cos theta the whole square. Now what next? We'll just take the constants on one side. So what we get is mr square by 2 pi, which is the unit, and the rest is unitless, cos square theta d theta integration. So that's your I. The theta is going from 0 to 2 pi. Now I hope you remember how we managed to do a cos square theta. We wrote cos square theta in linear angle using the fact that cos 2 theta is equal to 2 cos square theta minus 1. So we had cos 2 theta plus 1 divided by 2 as our cos square theta. So this also we can write it as half and cos 2 theta. So what we will have is mr square by 2 pi 0 to 2 pi 1 by 2 plus cos 2 theta by 2 d theta. That cos 2 theta by 2 gave us a 0 because it gave us sin 2 theta and whatever outside. So sin 2 theta with a 0 as a limit in theta. So sin 0 is 0 and sin 2 theta, if we put theta as 2 pi, so we will get sin 4 pi, which will also give us 0. So only the half in this integration is useful. So half times d theta. So half goes outside, and what we get is mr square by 2 pi, half comes out, and your theta integration from 0 to 2 pi will give you a 2 pi. So what we have is, we have this 2 pi getting cancelled with 2 pi, and we get mr square by 2, which is this. So obviously doing this was a bit of a headache, and even if it was not, it is not required if you know the theorem. So the theorem works very well. So we have just cross verified using integration. So absolutely not required when the question is asked. So I'll give you one another question to quickly get me the answer. For a disk of mass m and radius r about an axis which is along the diameter id through the cm, idcm is equal to how much? And why not one more for a sphere, say solid, through one of the diameters, mass is m and radius is r. So 30 seconds for it. So I hope you got it. Again, this disk qualifies for a laminar body. It has got no depth. So again, we'll say that I through this diameter and that diameter would be same. So twice of ID will be equal to Iz, which we already know is mr square by 2. So what we'll get over here is your ID will come as, twice of ID will come as mr square by 2. So if you take the 2 down, we'll get 1 by 4 mr square. So again, half of your Iz, as this one came, half of the Iz value, half of Iz, here also half of Iz. Now this one, I hope you got the catch over here. The body doesn't qualify, the sphere doesn't qualify for a laminar body for the perpendicular axis theorem. So you can't say that your ID plus ID is equal to that ID. In fact, all the three IDs, which is your 2 by 5 mr square, will be same. Your Iz is 2 by 5 mr square, your Ix is 2 by 5 mr square, and your Iy is also 2 by 5 mr square. So don't do the folly of adding your Ix plus Iy to get Iz, which will be absolutely wrong, as shown you in the case of the cube. So this is your perpendicular axis theorem. The concept of where to apply and where not to apply your perpendicular axis theorem cannot be better emphasized than doing this question, which was a previous year IT mains question. Suppose you have a cylinder. So your radius is given to you, r is given, your length is given to you, the cylinder's length is given to you, the mass is also given to you. Mass is, suppose m is the mass, and they have asked you what would be the moment of inertia about an axis which is passing through the center of mass of the body, like this. It is along a diameter of the cross section at the central part. So what is this ID? Now how to do this? So we'll quickly go through how to do this, but the point over here, what in fact I'll do this after a while. The only thing I want you to answer is whether this perpendicular axis theorem can be applied or cannot be applied in this question. So I hope you got that. The answer is it cannot be applied. It cannot be applied because your body is not a 2D body, and your ID plus ID this plus ID that will not be your Iz. Your Iz, which is going through the axis, is known to you. It is if it is a solid cylinder, it is mr square by 2. That's your Iz. But your ID, this one and that one, ID plus ID dash or ID will not be equal to Iz because it is not a 2D body. So in fact, people have done error of applying this and getting an answer which I think was in the option. So that's a wrong approach. So you'll have to actually do an integration for this to get your answer. So we have made the concept clear of where to apply and where not to apply a perpendicular axis theorem. I'm just in two minds whether I should do this question for you or leave it up to you to do. So I guess since it is on the board, I'll give you 5 minutes to do the thing. Pause the video and try it. Suppose you are not getting a start, then you unpause it. I'll give you a hint of how to do, and again pause and try further, and then you go on to see how it is solved. Yeah. So the hint is you'll have to take elementary masses which are like a disk having a very small width of, say, dx is the width, and that's your elementary mass. So that elementary mass is having a distance from the CM of x. So we know the moment of inertia of about the diameter of the elementary mass, that is dId. This is what we know. And then what is the moment of inertia of this elementary mass about this axis, about the central axis. So what will that be? You'll do a parallel axis theorem on that. So to get your DID, you'll do a perpendicular axis theorem, but then it's a known value now that it is, how much will this be? 1 by 4 this elementary mass dm times 1 by 4 times the mass of this thing times radius square. That is about the diameter of this thing, and then you shift it parallelly to this axis. So you'll get the moment of inertia about the elementary mass. You'll get the moment of inertia of the elementary mass about the center of mass of the body. So about the cm of the body you'll get, which will be equal to about its own axis, and so it is its own cm. So you can just call this one as, I'll call it as capital D. So to get that, you do about its own axis and then your shift, parallel axis shift. So how much is that? dm times divided by total volume, which is pi r square into L, into the volume of the elementary mass, which is pi r square into dx. You could have also said that the total length is L and you want for a dx length. So m by L into dx would have been enough. So which you can see over here, pi r square gets cancelled. So m by L into dx. So that's your dm. M by L into dx is your dm times r square plus again your elementary mass, which is m by L into dx times the distance square, which is your x square. So what we have is, we have m by L common, and then you have r square by 4 dx plus you have x square dx. So the whole ID would be integration of this going from minus L by 2 to plus L by 2. So I'll just integrate this, put the integration sign over here. So what do we get for the first one? M by L and then r square by 4 was earlier, and you'll get a L by 2 minus of minus L by 2. So you'll get a L by 2 plus L by 2. So that will result in L. So that is what you get from the first one. Your integration is x, upper limit L by 2, lower limit minus L by 2. The other one will give you L by 2 whole cube by 3 minus L by 2 whole cube by 3. So you have 1 by 3 outside, and you'll get twice of L cube by 2 cube, which is equal to, you will have 1 L getting cancelled from inside. So what you have is m r square by 4 for the first term, and the second term you'll get one of the 2's cancelled, and then 4 into 3 it is, so I'll just put the 4 outside. So you have 4 from here also, 4 from there also, I'll put the 4 outside. So r square plus you have L square by 3. So that's your answer. Now suppose I have to see whether I have done any mistake in the answer or not. That is what I have told you earlier also, some simple analysis when you have done a question which is having decent number of steps. So anywhere you could have landed into a mistake, a small mistake, what you say as a silly mistake. So a cross check would be if the radius was very small compared to the length. If the radius was very small compared to the length, the question looks like this. So that becomes a thin rod, and your I across the center of mass of the thin rod, we never cared whether it is going through the diameter of the cross section or not, because it was so thin that it was assumed that the cross section was assumed to be a point cross section itself, a point thickness itself. So that in fact the value what we used to do, m L square by 12 was the value for moment of inertia of thin rod. So this should give you the same if I say r is very small compared to L. So when I say r is very small compared to L, what do we get? We put r as 0 and we'll get ml square by 12. So thank God it is coming all right. So that's your answer. So that's an example of using your perpendicular axis theorem first to get your ID, which gives you 1 by 4. That 1 by 4 came through your perpendicular axis theorem, and then parallelly shifting it. So your parallel axis theorem is also taken care. So it becomes a nice demo of both the theorems involved, and it was asked in IIT mains. So you have to do at least this much to get the answer. So doing the process, the number of steps is never too high in physics question, but the thought behind it, since I have just orated everything, it is quite simple to follow, but the same thing has to come from you and in the exam pressure. So to get that in the exam environment, you have to be very comfortable with the concepts and very solid with your fundamentals. So I think that's it for the perpendicular axis theorem.